Hey everyone, today we're going to take a look at probability distributions. A probability distribution is really just the listing of all of the probabilities for an event, especially when there's multiple outcomes for that event. It has to be an event that is referred to as discrete, meaning it's something that I can count, as opposed to a continuous event where things could be divided up infinitely, such as time and temperature. But when we're talking about probability distribution, as long as you can account it and it's discrete, we can not only put together this distribution, but we can also figure out what's referred to as expected value, which in some cases is very similar to the average. So I am going to do an event where I flip a coin 5 times, and I want to know the probability of heads. Now, when you flip the coin, regular coin, 50% chance that it could be heads or tails on any of the coin flips. I want to do this 5 times, and I'm going to make a distribution for that. So here I'm going to have x, and x could be 0, 1, 2, 3, 4, or 5 heads as I'm flipping the coin. Now, for each one of these, in order to complete the probability distribution, I have to list the probability of x. Like, what's the probability that this is going to happen? Now, when I'm doing this, I am going to be using a formula that is going to take a combination of events and how many times am I looking for it. So in this case, I'm going to say, what's the probability that I flip the coin 5 times and I get 0 heads? So combination of 5 events taken 0 at a time. And I'm going to do that for each of these. So as I go down through here, here's 5 combinations 0, 5 combinations taken 1 at a time, combination of 5 things taken 2 at a time, so on and so forth. Now the reason I'm doing the combination is because if I think about how many different ways are there to get 2 heads, for example, I could have heads, heads, tails, tails, tails. Now technically within those 2 heads, I could switch the order around. But a combination of events says that the order really isn't important. When you take those 2 heads, doesn't matter if the first one is a 1969 coin and the second one is a 1970 coin, those are the same outcome, getting heads on the first 2. So that's why we're doing combinations instead of permutations. Just a quick recap for both permutation and combination. They start out by saying I am going to take the number of events, 5, divided by, if I'm doing the combinations 2, how many times are you looking for? Now this would be the permutation, 5 factorial divided by 3 factorial. For a combination, I throw that 2 on there again, basically to say these 2 things, I need to divide that out because I can take them in either way. So this is 5 combinations taken 2 at a time. I'm going to do that for all of these things. And what I'm going to find out is that if I do 5 combinations taken none at a time, there's really only one way to get all tails. In the same way, there's only one way to get all heads. So if you do 5 combinations taken 5 at a time, you're going to see the same thing. When I do it 1 at a time, in both cases, same number of outcomes. And so I'm listing the outcomes here. I shouldn't list this as the probability of x. I'll change these in just a second. But there's 5 ways in order to get it 1 head, and there's 5 ways to get 1 tail. And the same thing, I would keep going and find out that it's 10 ways to get 2 heads and 10 ways to get 3 heads. So this is where these probabilities that I'm about to list are going to come from. So I'm going to erase those because this should be the probability. The thing that I have to remember too is that when I'm flipping a coin 5 times, the first flip I have 2 outcomes. The second coin flip there's 4 possible outcomes, and then it goes down to 8 and 16 and 32. This keeps breaking up. So really I have 2 to the 5th. There's 2 outcomes. I'm going to do it 5 times. So 32 total outcomes. So these are my probabilities. 1 out of 32, what was this? 5 out of 32, 10 out of 32, and then you saw that pattern before. It kind of repeated itself. It was symmetrical in this case. And those are the probabilities that I have. This is a probability distribution. It's discrete events, things that I can count, and I've got all the probabilities listed for each one. Now, to make it a valid probability distribution, these probabilities must add up to 100%, or 32 out of 32, or just the number 1. So if I'm adding these together, 1 plus 5 is 6, 16, 26, 31, 32 out of 32 if I take the sum total of those things. So that is how you build a probability distribution. But let's take a look then at expected value. The expected value formula is going to really be a sum. So let's do the expected value of x is going to really be the value of x times the probability of x. I'm going to do that for each one of these individual items here. Each x times the probability of x, and I am going to take the sum of all of those. So really the expected value formula is just the sum of each x times its probability. Now the key in here is, what is the value of x? In a lot of cases we would say the value might just be itself, like how many coin flips you have. Sometimes when we are working with things, each of these values has maybe a dollar amount attached to it, like this is the actual value. So I'm going to do that both ways when I look at this. The first way, I'm just going to say that the value of x is 0, 1, 2, 3, 4, 5. And I'm going to get the expected value for flipping the coin 5 times. This is basically saying like you get 0 points if you get 0 heads, and each head you get is worth a point. If you get 5, you get 5 points. So to do that, I would take each of the x's and multiply it times its value. So I'll make a column over here. Here's x times the probability of x. And I just multiply these. That's 0, that's 5 out of 32, this is 20 out of 32, 30 out of 32, 20 out of 32, and 5 out of 32. And then I would add all of those things together. 25, 55, 75, 80 out of 32. And 80 out of 32 gives me an expected value, if these were points, of about 2.5. Which probably makes sense. You're going to get 50% of the time you're going to get heads, so I'm expecting the value to be 50% of this. Now there's another way to do the expected value with this, and that is to say, what if I assigned each of these some sort of monetary value? So for example, let's say that I make a bet, and I say that if you flip the coin 5 times and you get 5 heads, I am going to pay you $10. If you get 4 heads, I'm going to pay you $3. If you get 3 heads, I'll pay you $1. 2 heads, we break even. 1 head, you owe me $5, and no heads, you owe me $9. So basically, you flip 5 heads, I give you 10. You flip none, you give me 9. That's what most people are going to see in that. And I just made these numbers up to try and look somewhat promising for you, but my curiosity would be, if I'm going to play this game, what's the expected value? Now obviously I could play once and I could win anywhere from 10 to losing -9, but I want to know what's the expected value if I were to play this game over and over and over again. Really, the average winning. So a lot of times I think, if you're thinking in the gambling terms, expected value is kind of like the average winnings for each time you play the game. In this case, I still do the same work. It's just, instead of multiplying this x that's in the expected value formula, instead of multiplying the value of 0, 1, 2, 3, 4, 5, I'm going to multiply the average winnings times each of those x's. Now, this is also where, in order to kind of speed things up, I tend to do this type of work in Excel. So let me pull over a distribution for this. All right, so I've got my Excel spreadsheet here. I'm going to fill out the things that I have already for a couple of reasons. But here's X, here's the probability of X. Then I'm going to put the value of X. I'm going to use a lowercase x for this. You could just label it however you want, but I had 0, 1, 2, 3, 4, 5. And then for the probabilities, I had 1 out of 32, 5 out of 32, 10 out of 32, 5 out of 32, and 1 out of 32. So one of the problems that I have with Excel right now is that these things that I just put in, those aren't really numbers. It actually is probably thinking this is some sort of weird looking date. This is just text. When I put that in Excel, I really should have put in a division sign. It's going to turn these into decimals, which is fine. Just shows the percent of each one of these. So I changed these all to actual numbers by simply typing in the function of equals. Now I'm going to put in the value for this. This is -$9, -$5, 0, 1, 3, and 10. And so you can see what's happening here. I'm going to do this manually. I'm also going to do a shortcut for it as well. But here is the X times the probability of X. That's the value times the probability. In each one of these cases, I am just going to do equals this times this and see how much I would really win for all that. And then I'm going to grab this corner and drag it down so that I've redone this for all of them. Because this is dollars and cents, it's nice because there is a built-in way to format things as money. So I'm going to click on that. It automatically rounds it off to 2 places for me. There's also formulas if you wanted to round it off to different number of places. But that is X times the probability of X. The expected value of X is really just the sum of that column D I'm just going to write for right now. It's the sum of all of those things that I just put together. So I'm going to do sum of column D and make that $1 and cents. With this setup, it's telling me positive 3 cents. Every time I play this game, I'm expecting to win 3 cents. Now I'm going to win more, I'm going to lose more, but on average, over thousands and hundreds of thousands of times playing this game, I'm going to win 3 cents a game. That means this game is really set up in my favor as the person flipping the coin and trying to get heads. And yeah, I could lose $9, but I could win $10. Now you can see with the power of Excel, if I change a few of these things, and let's say if you make it perfectly even, and not even perfectly even, but going and putting a -10, -5, 0, 1, 3, 10 as the payouts, the expected value is 0. So I would imagine that someone in any kind of gambling industry is going to know these payouts and get this ever so slightly into the negative column for the player. An example might be doing something like this, and changing some of these numbers and saying like, oh, I'll even pay you, let's say 25 cents in that case, or 50 cents I'll pay out. This one comes back to even, so you could make it look like, hey, you could win 25 cents, $1, $3, $10. You could lose 10 and 6. And again, you could change these numbers however you wanted to kind of see what are the different types of payouts to make it look more attractive to the person playing. But that is expected value. The shortcut that I wanted to show is that expected value in Excel is really just taking each of these numbers times its partner and then adding that up. That's referred to as a sum product. When you do a sum product, you would tell the things like, hey, I want the sum product of everything in column B times everything in column C. And as you're working through that, you'll notice that I have the same answer. It just goes and matches everything in column B times column C and then adds together all those results. So it saves you one step in here as you're working through it. But that is the expected value, sometimes referred to as the average. So if you're going to do probability distributions and then get into variance and standard deviation of a probability distribution, that is where you start, finding the expected value, the mu or average. So hopefully that helps. And I will be putting together another video on exactly what I just said, variance and standard deviation.